right, welcome back. In this video, we are going to be building off of the linear kinematics discussion that we had previously and start our dive into graphing of linear kinematics. And so most of where we are going to start today is going to be with an example that you would have found in the last slide of your linear kinematics PowerPoint. On that slide, it would give you an example of an elevator moving up and down. And that's where we're going to start today with our examples. And so a few important things to mention as we get into the graphing points of this. My goal as we go through this process is to trick you a little bit into doing some pretty simple calculus with me that you will have no idea that you are doing. All I'm going to ask you to do is just draw some lines along with me as we start into these basic examples. And so, again, the example that we are starting with is found on that last slide of your linear kinematics PowerPoint, graphing of elevator motion. What we are starting with is we are going to be graphing purely vertical motion, so just up and down motion of that elevator as it moves. We are going to graph its position changes, velocity changes, and then its acceleration changes throughout the movement of the elevator. Now, a couple of other notes as you read that. The way that it should read is that you are going to get onto an elevator at the bottom floor. You are going to ride that elevator up to floor number 4, where it will then stop. You have some people in, some people out, doors close again, and then you continue from the 4th floor all the way up to the 8th floor, where you stop again. Then you realize you've forgotten something all the way back down, and you proceed to go back from the top 8th floor all the way back down to the bottom floor where you started. And that's going to be the entire process that we graph out of the elevator. Now, there is some other filler in that problem that you will see about how much people weigh and people getting on and people getting off, a lot of stuff like that. For this first example, we are ignoring all of those components. So anything that would make something move faster, move slower, anything like that, we are ignoring for now. The purpose of this first graph that we are going to do is get you the very basic, bare bones of these graphs. So we are going to make assumptions that all parts, all phases of this movement is going to take the same amount of time. Hopefully that will make some more sense as we get a bit further into this process. After this one, we'll start to dig in a little bit more of making things faster, making things slower, and talk about what that looks like. But for this first example, all phases of moving up and down that we'll talk about, we are going to assume take the same amount of time. So any of that extra little filler in the word problem, again, ignore for now. So, as we get started into our first example, let's go back a little bit into your linear kinematics PowerPoint previous to this, and there should have been a couple of key considerations that we mentioned before a kinematics problem. And so with that, a quick reminder even that kinematics as a whole, remember what we are studying is how things are moving. So kinematics is a branch of mathematics studying how things are moving. And so that's going to tell us how far something moves, how much the elevator moves, how fast does it move, velocity, and whether or not it's speeding up or slowing down, accelerations. All descriptors of how motion is occurring is kinematics. And within that, you were introduced to some preliminary considerations. There were the two big ones discussed were, what is moving and what is it moving in relation to? So we're going to ask those two questions before any of these problems. It's because it's going to set up our reference frame of these graphs, especially our position graph where we start. So, as we get into that, for the first example of the elevator, we are going to have what is moving, hopefully pretty simple, it's the elevator. So that's the thing moving that we are interested in its motion. What it's moving in relation to, for this example, we're going to set to that bottom floor where we start. That will change a little bit based on other examples that we get to. More on that later. But for now, we are setting up this problem with what is moving, our elevator of interest. It's moving in relation to the bottom floor where we start. The importance of that is what we set it moving in relation to represents the 0 on our first graph. So that brings us to the first of our graphs. We are going to work through in order first our position graph, then we'll build from there into the other two. So your first graph, it's going to be your position over time graph. The axes for this version of the 3 graphs looks very typical of most graphs you have seen. You have your y-axis, and then you have your x-axis along the bottom. On your y-axis, you are going to have the variable of interest of the graph. For this one, that is going to be position. We will use the traditional units of meters for this graph, and this is going to be position changes over time. And we'll just do that in a generic seconds of time. So we have changes in position over time for our first graph. Now, what we said a second ago, what we're setting it in relation to, that represents this bottom corner down here. So at the very beginning of the movement, when time starts and the movement starts, what is 0? That for us will represent the bottom floor. Okay, so that's what we're saying. What is it moving in relation to? That tells us what is represented down there at 0 of our graph. Now, in the position graph, we are going to build this out every single time using a series of 3 types of lines. The 3 lines that you will see. We have line number 1, line number 2, and line number 3. Now, for each of these, as you look at them, you are examining these going from your left to right, following these lines. And we're going to ask a few questions about each of these and describe what they do in a few different terms. Depending on who you talk to across campus or across fields, whether it be mathematicians, more applied scientists like exercise scientists and biomechanists, you'll hear these terms described differently. So let's hit on a few of those touch points with each of these. As you look at lines 1, 2, and 3, going left to right, line number 1, as you follow it left to right and it starts to go up, one thing to note on that one is as it goes up, that line is getting steeper as it goes up. When we say it's getting steeper, that tells us a few different things. Number 1, it tells us that the slope of line number 1 is increasing over time. So line number 1, its slope is going up over time. If you ask a lot of mathematicians how they would describe that line, they would refer to it as what is known as an exponentially increasing line. Fancy. What that means for us is it is going to represent something that is speeding up. So line number 1, getting steeper, the slope is increasing, and it represents something that is picking up speed. So it's getting faster as it moves. Line number 2 is a straight line, its slope is constant as it moves, and it is moving at a constant rate. So line number 1, getting steeper, picking up speed. Line number 2, unchanging slope, moving at a constant rate, which then brings us to line number 3. As you follow it left to right, instead of getting steeper like number 1, it starts to flatten out as we go instead, meaning the slope of line number 3 decreasing. Mathematicians would refer to that line as an exponentially decreasing line, and it is going to tell us that something is slowing down as it moves over time. So line number 1, increasing slope, picking up speed. Line number 2, moving at a constant rate. Line number 3, decreasing slope, flattening out, and tells us that an object is slowing down as it moves over time. These 3 are what we are going to use to build out all of our position graphs. Maybe just altering their shape a little bit, but those 3 lines are how we're going to build everything. So keep these 3 in mind. I'm going to erase them so I have some room, but we're going to reference back to them a lot. So keep in mind what those 3 look like. Now, let's talk about your elevator example. Again, this is found in that last slide of the Linear Kinematics PowerPoint, the example of the elevator moving. Remember our first part, we are starting at the bottom floor, and we are going to start moving up. So picture it for yourself. We're graphing the elevator motion relative to that bottom floor. So we're going to start down here in the bottom, at the bottom corner. You get on the elevator, push the button, boom, doors close. And then how does an elevator start to move? It doesn't just immediately start moving at one set speed. It's starting from 0. It has to start picking up some speed as it goes. So if it starts from 0, not moving at all, and starts moving in any way, it picked up speed. Think of it if you're in your car in the parking lot, you go to leave and you go from 0 miles an hour even to 1 mile per hour, you sped up. Meaning we are going to start with line number 1 of our 3 lines. So down here in our bottom corner, we're going to have a line number 1 representing increasing slope. It's getting steeper as it goes up, representing the elevator starts moving and picking up speed as it moves. So it starts moving and it is getting faster as it moves up. Now, as you're on the elevator, it doesn't just speed up forever. Eventually, it's going to get to the speed that it is trying to get up to, and then it's going to just stay there for the middle portion of this ride. So once it gets up to speed, throughout the middle portion of this movement, I'll exaggerate it some, we will have a constant straight portion of the movement. So the elevator is still moving up, time is still passing, it's just moving at a constant rate. And then as we start to get to our first stop, floor number 4 for the elevator, we're going to have line number 3. It's going to start to flatten out, eventually coming to a stop. So once this has totally flattened out, we're not going up or down, no change in position, but time is passing, so we have now come to a stop at our first stopping point in the example, the 4th floor on the elevator. So we started moving, pick up speed, constant speed throughout the middle portion of the ride, start to slow down, and then come to a stop at our first stopping point, the 4th floor. And this is how most of our phases of movement up and down are going to look. We're going to have a period of speeding up, a constant in the middle, and then a period of slowing down. What we'll start to play with in the timing later is how long each of these phases take. But we're always going to have a phase of each of these as we go. Also, make sure you are numbering these along with me. That will be important as we start to get a bit further into this. You'll see why. So now we're stopped at the 4th floor. Remember, in that one, we are now stopped. In the example, it has us just sitting there for a few seconds while people come in and out of the elevator, so time is passing, but we're just sitting there not moving, waiting to go in. Once everybody's in and out, we start the second process. We're going to go from floor number 4 up to floor number 8 of this example. And so think about that one. We're assuming all timing aspects of this take the same amount of time. We're going, instead of 1 to 4, we're going from 4 to 8. So we're going the same amount of floors in the same amount of time. So these next set of lines, they're going to look exactly the same as what we just did, because the elevator is doing the exact same thing that it just did. So it's going to start moving again, picking up speed, getting steeper. It's going to have a constant portion through the middle, and then it's going to start to slow down as it gets to the top, where it will again stop at the top floor of our example. So lines 1, 2, and 3 are going to be exactly the same as lines 5, 6, and 7, because we're doing the exact same thing. Our elevator is going up 4 floors, then it stopped, then it went up 4 floors again. So same movement, same timing, same lines. Now, in the example now we're at the top, we've forgotten something, we realize that, we're going all the way back down to the bottom, so I'm going to expand my x-axis here a little bit for that. Now, we're going to start going down in our position graph. Our 3 lines that we were working with, those still apply, we just need to invert them, so instead of going up, we're going down. We're still going to have lines getting steeper for picking up speed, straight lines for constant, and flattening out for slowing down. But now, for number 9 here, our elevator's not moving, so it starts moving down, picking up speed. So instead, our line getting steeper is now just going down. From point 9 through the middle portion of this ride, we have a constant period once it is up to speed. And then as we start to get all the way back down to the bottom, that line starts to flatten out and eventually come to a stop at the bottom. So again, you still have, just like lines 1 and 5, the line getting steeper, picking up speed, but at number 9, it's just going down instead of up. Same with number 10, and same with number 11. And so in the position graph, a couple of notes that you can tell. When I ask you which direction things are going for the position graph, that's a pretty easy reference. It is simply, is these lines going up or are they going down? For these lines that are going up, all of these first processes, positive direction, going up. Positive direction, moving up. As we start to get into the downward phase, 9, 10, and 11, the lines simply are moving down. Okay, so the direction of the position graph lines, they are simply what direction are the lines going in the position graph. And we're going to need that as we start to build these out into the next graphs after these. So, what we have now are graphed out phases of changes in position over time. If you think back to your Kinematics PowerPoint and lecture previous to this, remember that changes in position over time are either speed or velocity. In this scenario, we have directional components, up or down, so we're working with velocity. So changes in direction, or changes in position, over time, velocity. So we use this graph to build the next graph velocity. So, that one's going to look a little bit different as we go. For the velocity graph, you have your y-axis, and then your x-axis is in the middle of those graphs. So unlike here, where we had pretty traditional axes, the velocity graph, you've got your y-axis, which is still going to represent our variable of interest, velocity. We'll use traditional meters per second for that. And these are still going to be changes over time in seconds. So velocity over time. But now in the middle, our x-axis, that is there because that represents our zero, because we're going to have positive and negative velocities. So everything on the top half of this graph, everything above zero will represent positive velocities. Everything on the bottom half, below zero, represents negative velocities. And remember, importantly, when talking about velocity, talking about these kinematic values, the sign of these velocities, positive or negative, tells you one thing and one thing only: direction. That is all it tells us. A positive velocity means you are moving in the positive direction. A negative velocity means you are moving in the negative direction. That is it. That's all the signs tell you of velocity, is the direction we are moving. Now, our job is to use this position graph to build the velocity graph. We numbered all of these phases for a reason. Every numbered phase in this graph has to correspond over there. So we have to have matching chunks in every single graph. It serves as a bit of a cheat sheet for you to make sure you've got all parts included. Let's talk about how we do it. Part number one of our position graph. First thing we're going to ask is, what direction are we going in number one? Remember, for the position graph, look at the line. It is going up. So that tells us we are moving in the positive direction. So we're going to have a positive velocity. And what are we doing in part number one? Are we picking up speed, slowing down, or moving at a constant rate? Remember line number one, it is getting steeper. That slope is increasing. It tells us that we are getting faster. So, we're getting faster in the positive direction. Now we come over here to the velocity section. The way that will look is we're going to be on the top half of this graph, and we are going to be speeding up, meaning we're going to be getting further away from zero. Our magnitude of velocity is increasing. So how that looks, we're starting here at zero. We're going to have a diagonal line going up, away from zero for number one. So top half, positive direction, tells us that we're moving up, getting further away from zero, meaning we are picking up speed. Now I want you to get in the habit of saying it in that way. Think about it again as the speedometer in your car. If you get in your car and you are sitting there in park, it'll be at 0 miles an hour. If you start moving, it's going to start to tick up. 1, 2, 3, 4, 5 miles an hour, 20 miles an hour, 80 miles an hour, getting further from zero as you get faster and faster. Okay, so always think about it in those terms of top half or bottom half for the direction, and then am I getting further away from zero, speeding up, or am I getting closer to zero, slowing down? So for part number 1, corresponding to part number 1, positive direction, picking up speed in the velocity graph. Number 2, positive direction still, moving up, but moving at a constant rate. So the velocity, we are now in cruise control, is not changing. So we are still moving, we still have speed, but it's just not changing over time. So moving, constant rate, constant positive velocity for part number 2. And then finally, phase number 3. Still moving up, still in the positive direction, but now we are starting to slow down. So for that one, we're still on the top half because we're still moving up, positive direction, but we are slowing down, which means we're going to be getting now closer to 0. And so that one is going to be coming back down to 0 for number 3. And once we get back to 0, again, think about it as your car. If you are slowing down at an intersection, you come to a stop, you're going to look down, 0 miles per hour. Okay. So once you get 0, you are now stopped. So picking up speed for number 1, constant for number 2, slowing down for number 3, and now we are matching there at number 4, not moving at all. So time is passing, we are not moving, line number 4. Okay, so right on 0 for number 4. 5, 6, and 7. Remember, we're doing the same thing for these. So these lines will look identical again. We're going to start moving in the positive direction. We're going to have a constant period through the middle. And then we're going to start to slow down all in the same direction for 5, 6, and 7. Again, because all of these assumptions are that we're taking the same amount of time for these phases, these 3 and these 3, we're doing the exact same thing in the exact same amount of time. They look the same. Again, we will play with some of these timing aspects in the next couple of examples. But for now, same movement, same amount of time, same lines. Now, we're back up to a stop at the top floor for number 8, not moving. I'm going to get rid of my timing units there so I can finish this one out. Now for number 9, look at the position graph. What direction is that line moving? It is now going literally down, meaning we're moving in the negative direction, and our velocity is going to be negative on the bottom half, and getting steeper, speeding up, so getting further away from 0. So now, further from 0, but in the negative direction. For this one, again, think about it as we're getting further away from 0, meaning the magnitude of the velocity is increasing. We're just moving in the opposite direction. If we lived in fantasy land for these things, if with the car example still, this would be if you put your car in reverse and start moving and hit the gas, that your speedometer would just be a negative number as it ticks up from 0, that you're moving backwards instead of forward. So further from 0 still represents picking up speed for us, and on the bottom half of this graph simply tells us that we are moving in the negative direction or down. Number 10, still moving at that constant rate in the negative direction. And for number 11, still moving in the negative direction. This line is still going down, but as it is flattening out, we are slowing down, meaning we are going to be getting closer to 0, so coming back up to 0 and to a final stop. Okay? That's our velocity graph of these. And so now we've used the position graph to build the velocity graph. Now, with this one, we have phases of changes in velocity over time. Think back to kinematics. What did we define as a change in velocity over time? Accelerations. So we use the velocity graph to build our final of the three, our acceleration graph. And that's what we're going to do next. I'm going to erase this position graph, so I've got a little bit of room left to finish out, and we'll talk about our last of the three. Now, a couple of notes as I get this one set up for us. The acceleration graphs, the first time people see them, always look a little bit funny. And so bear with me as we introduce them, and I'll explain all of them as we go. Each acceleration that we graph is going to be represented by simply a dashed line on the graph. So when we say a positive or negative acceleration, whatever it might be, it'll just be a dashed line on the graph. And then we'll have a series of vertical lines as well in the graph that will simply serve as connectors between the different accelerations so the graph looks clean and pretty. This will make sense as we start to draw it, but no, it looks a little different than all the other graphs. And each acceleration that we care about is graphed as these dashed horizontal lines. So let's draw one of these out. The axes for acceleration look like the velocity graph did. You're going to have your y-axis and x-axis in the middle, again representing 0 in the middle, because we can have positive and negative accelerations. On the y-axis, variable of interest, acceleration, traditional units, meters per second squared. Again, over time in seconds. So now we are looking at acceleration changes over time. Again, like velocity, everything on the top half above 0 will represent a positive acceleration. Everything on the bottom, negative accelerations. Okay, so positive and negative accelerations. Please reference back to the previous lecture on your 4 cases of acceleration that we've talked about. They're going to be very important going through this process of these graphs. So, going through again, every corresponding number of the graphs has to translate to the next graph. And we go through them one by one. Line number 1 of the velocity graph, we ask the 2 big important questions for acceleration. What direction are we going? And are we speeding up or slowing down? For number 1, direction is positive. We know that from the velocity graph because we are on the top half of the graph. Positive velocity means positive direction. If you look at your position graphs, you would simply say the line is moving up for direction. So positive direction, doing what? Speeding up, because we are getting further away from 0. So we're speeding up in the positive direction. Think back to your 4 cases, speeding up in the positive direction. What kind of acceleration is that? Positive acceleration. So we come back over here, we're going to be on the top half. Again, dashed line to represent part number 1 of a positive acceleration. For now, how high we draw this does not matter, because we're not making any references to big acceleration, small acceleration, things moving really fast, things moving really slow. None of those nuances yet, just simply a positive acceleration. More on that soon. Number 2. Positive direction on the top half, but what are we doing with the velocity? Constant. So, if velocity is not changing over time, by definition, our acceleration is 0. Because remember, acceleration is a change in velocity over time. We don't have any change in velocity over time. We're moving at a constant rate, so acceleration, 0. Number 3, direction. Top half, positive. So positive direction, doing what? We're getting closer to 0, meaning we are slowing down. Slowing down in the positive direction. What kind of acceleration is that? Negative. So we're going to come down into the negative half and have a negative acceleration. Again, each acceleration, positive acceleration, 0 acceleration, negative acceleration, all represented by those 3 dashed lines. These verticals, they're just there to make it look clean and stair-step from one to the other. They themselves don't mean anything. They're just connecting everything together for a nice, clean graph. Phase number 4, remember what's going on there. We are now stopped. The elevator is not moving, so if we are not moving, we have no velocity. We certainly have no acceleration. So we're back to 0, not moving. And one last time to make sure I annoy you with it, parts 1, 2, and 3 are exactly the same as parts 5, 6, and 7 because we're doing the same thing. The elevator is going up the same amount of floors in the same amount of time, so the kinematic description of those phases is the same for each of these. Please let me know if that doesn't make sense as to why, and I can explain it further if need be. But we're going to have for number 5, again, speeding up in the positive direction, positive acceleration, moving at a constant rate for number 6, so 0 acceleration, and slowing down in the positive for negative acceleration with number 7 until we get back to a stop, not moving, for number 8. So again, the same lines for those 2 phases as we are describing this motion. Rounding us out, number 9. Direction that we are going. Bottom half of the velocity graph, meaning negative velocity, which tells us negative direction. If you had the position graph in front of you and asked how you know, you would say the line is going down. Careful with that in the velocity graphs, because that's not always the case. For the velocity graph, knowing how the direction is going, you're just looking at top half and bottom half, not line direction. So be careful with that. Always top half or bottom half. Here, bottom half, negative direction. Doing what for number 9? Getting further from 0, meaning picking up speed, getting faster. Getting faster in the negative direction. Back to our 4 cases of acceleration. Speeding up in the negative direction. Negative acceleration. So speeding up in the negative, it's a negative acceleration. Again, the height of these doesn't matter for now. We'll change those coming up in a few more examples. Number 10, constant velocity, so 0 acceleration. And number 11, finally, negative direction, bottom half, getting closer to 0, slowing down. So we are slowing down in the negative direction, our last of the 4 cases of acceleration. Slowing down in the negative is a case of positive acceleration. And that is your acceleration graph. Again, the first time you see these, they look a little funny, just different than the other ones. Again, each horizontal dashed line is the acceleration itself being represented. All the vertical lines simply are just connecting it together, so we don't just have a series of random dashes throughout the graph, and it makes it look much cleaner and easier to follow. Next, we're going to do a couple of examples, changing this up a little bit now from those assumptions that we've made. So, all the graphs that we're going to do will follow these same basic shapes of the position graph and how it was drawn out with its lines, the velocity graph with these types of lines, and the acceleration graphs here. All that will start to change now is just how we kind of stretch out or smush together these shapes to make them represent something being faster, taking less time, or taking longer, being slower type movements. And so we're going to go through another example or two of these in the next video. We're going to bring these examples a little bit closer to home. Instead of an elevator moving up and down, we're going to talk through some exercise type motions and how they would look going up and down, and how they'll look if the lift is heavy in the movement, if it's speed work day and it's really light and easy to move, and how that will dictate the shapes of these graphs. So today we've gone through the position, velocity, and acceleration graphs of the vertical motion of the elevator example provided in your PowerPoint at the end of the Kinematics PowerPoint. If you have any questions about what we did in this one, please shoot me an email and let me know. Again, all of these, we were making the assumptions that all phases of the movements were taking the same amount of time. So there was no fast portion and slow portion. We're going to build on that in the next examples, in the next couple of videos. We'll get to that next time, and I'll see you then.